Dear students, in this video lecture, we will have discussion on laws of electromagnetic induction. The laws of electromagnetic induction are very much important in understanding the working of transformer, electric generator, and motor. The laws of electromagnetic induction are known as Faraday's laws of electromagnetic induction. So we'll study the laws of electromagnetic induction as Faraday's first law of electromagnetic induction and Faraday's second law of electromagnetic induction. It states that whenever the flux linking a conductor changes, or varies, an EMF is induced in the conductor. The EMF so induced is called as induced EMF. If the conductor in which EMF is induced forms a closed path, then current flows through it. Such a current is called induced current. For example, let us consider a conductor here and a permanent magnet. With polarity as shown here. Now if I take this bar magnet near the conductor, then more number of magnetic lines of force will link with the conductor. And if I take it away from the magnet, less number of magnetic lines of force will link with the conductor. That is, the quantity of the flux that is linking with the conductor is changing. So because of this change in flux linking with the conductor, EMF will be induced in the conductor, and that EMF is called as induced EMF. The flux linking with the conductor may be made to vary with respect to time in different ways. That is, either by rotating the conductor in magnetic field or moving the magnet to and fro, keeping the conductor fixed, or by moving the conductor to and fro in the magnetic field, keeping the magnet fixed. And if we have electromagnet, in that case, keeping the conductor fixed and electromagnet fixed only by varying the current through the coil of electromagnet, because we know that the flux produced by the electromagnet is directly proportional to the current flowing through the coil of electromagnet. So just write here, in the above figure, if bar magnet is made to move to and fro then the flux linking with the conductor varies and EMF gets induced in it. I will denote the EMF induced in the conductor as E here. If we form a closed path, then current will be flowing through the conductor, which is called as induced current. Because we know that for the current to flow, closed path is required. The change in flux linking with the conductor may be made possible in different ways. Given below. First one, conductor in the magnetic field. Second one, by moving magnet to and fro with respect to conductor. Third one, by moving the conductor to and fro in magnetic field. Fourth one, by varying current through coil of electromagnet whose flux links with the conductor. It was observed that when the direction of conductor with respect to magnetic field or vice versa was reversed, the direction or the polarity of EMF induced in the conductor was reversed. Therefore, we can write, if the direction of relative motion between conductor and magnetic field is reversed, the direction of induced EMF gets reversed. Now we will study the Faraday's second law of electromagnetic induction. It states that the magnitude of induced EMF is directly proportional to the rate of change of flux linkages. Let us say there is a conductor and at a time t1 flux phi1 links with the conductor, and say this flux that links with the conductor goes on changing with time this way, and at t2 flux phi2 links with the conductor. So what is phi1 here? Phi1 is flux linking with the conductor at time t1. Phi2 is the flux linking with the conductor at time t2. So let us write here. Let at time T1 second, phi1 Weber of flux links with a conductor and at time t2 second, phi2 Weber of flux with that conductor. Flux variation with respect to time is shown in figure above. Now change in flux linking with conductor in T2 minus T1 equal to T seconds. Here T means time axis. Is phi2 minus phi1 equal to phi Weber. If T and phi are very small, then we can write phi2 minus phi1 upon T2 minus T1 equal to d phi by dt. Then according to Faraday's second law of electromagnetic induction induced EMF E is directly proportional to d phi by dt and is equal to n into d phi by dt, where n is number of conductors. In the above explanation, single conductor is considered. That is, n is equal to 1 here. That is, n equal to 1. In addition to Faraday's laws of electromagnetic induction, there is one more important law, that is Lenz's law. It states that EMF induced in a coil or conductor opposes very cost to produce it. Therefore, a negative sign is shown with induced EMF. As given below. E is equal to minus n into d phi by dt. So this minus sign tells us that this induced EMF opposes very cost to produce it. The very cost to produce induced EMF is the change in flux linking the conductor or a coil. Therefore, induced EMF will oppose the change in the flux. Dear students, I will stop the class here and continue in next class with self-induced EMF and mutually induced EMF. Thank you.